Hey everybody, thanks for tuning in. So we're starting a brand new video lecture series on the expanding universe. And in this video lecture series, we're going to be addressing three topics. And so topic number one is, how do we know that the universe is definitely expanding? And number two is, knowing that the universe is expanding, can we predict what will be the future of our universe? And then number three, we'll be looking into the past and trying to figure out what was the universe like back then when everything began. In other words, I'm talking about the Big Bang. Okay, so now let's just jump right in, and in this video lecture series specifically, we're going to be addressing the first question. So when we're talking about the universe in the biggest scales, now that really belongs in a specific or separate subcategory in astronomy called cosmology. So just to clarify, this is not the same as cosmetology, which is a totally different field. So the definition of cosmology is the study of the universe and its components in the largest scales. So literally, you're talking about the universe. We can't really get any larger than that. And we ask, questions that are outlined in the slide. So how is matter arranged in the largest scale? So if you were to kind of just zoom out as far as possible, where you can see the whole universe in one picture, what does that actually look like? And then we look back into the past, talking about the history and the origins of the universe, asking questions like, how did galaxies and the largest structures you can possibly find, galaxy clusters, change over time? How do they evolve over time? And how did the universe actually start or begin? And then now looking into the future, what's going to be the ultimate future or the fate of the universe, knowing what we know about the past and the present? And so some people would argue that cosmology, as its own separate study, really started with Olber's paradox. And so Olber was a German astronomer that lived in the 1800s, and in 1826 he had this question. This was came to known as the dark night paradox. So if the universe is unchanging, infinitely old, and large, and filled with so many stars, then why is the night sky, and therefore space, dark? And so the way he thought of it was shown in this picture on the left, kind of like looking far into the forest of trees here, because you have to realize that when you're looking at a forest of trees, you can't really see what's beyond this forest because all of these trees are blocking your way. But if you look in your immediate vicinity, like whatever's in front of you, you'll find that maybe there's like one or two trees blocking your view as you're looking further out into the forest. But then as you look further and further and further out, then now you're actually including a larger amount of space in your field of view. So there's going to be more trees that are likely going to be in your way, blocking your view as you look deeper. And so ultimately the end result will be, the forest will appear opaque to you, because you have so many different trees blocking your view. So the same idea can be applied to space with the same assumptions that Olber had, right? It's unchanging, infinitely old, large, and filled with so many stars. So, this is what he thought of when he asked this question. In your immediate vicinity, you might have one or two stars, blocking your view the further out you look into space. But then now you're including a larger and larger volume of space the further out you look. So therefore, you're going to have more and more stars included in your field of view. And so therefore, it should actually be bright because each one of those stars are emitting a lot of light. But we now know that there's many things wrong about Olber's assumption. The universe is definitely changing. It definitely had a beginning. It's changing over time. And the stars themselves are also going to be changing over time as well. They're going to evolve. They're going to appear and disappear. Some of them will be white dwarfs. Some of them will be exploding into supernovae. And so really the short answer to Olber's paradox is that the universe did have a beginning. You have to kind of dissect his assumptions and prove that they're actually wrong. Okay? And the implication of the short answer here is that if the universe had a beginning, it will continue to evolve and change over time. Okay, and so with Auber's paradox out of the way, now we can actually start talking about some of the key results that led us to believing that the universe is actually expanding. And it all starts here with Vestal Slipher and his study of the spectra coming from galaxies in the 1920. So you can see a picture of Vestal Slipher here on the left, and then you can also see the spectra that he studied here on the right. And on the bottom here, you can see the laboratory reference. So if you take the spectra from a galaxy and you look at the absorption lines coming from that galaxy, you might see something here at the very bottom. And so now you compare this to the spectra of different objects, and you're observing the same element, but now compare this to a star, you might see them slightly shifted to the right. And you look at this for now another nearby galaxy. Now you can see a more significant shift to the right. For further and further away, you're just seeing this shift, getting more and more to the longer or the redder wavelengths. And so what he actually concluded was, hey, the spectra of the distant galaxies, all of them, okay, there's no exceptions here, all of them appear to be redshifted. And he even found that galaxies were moving away as fast as 1,200 miles per second. And so if you're Vestal Slipher looking at these spectra, you have to ask yourself, why? Why does that have to be the case? Okay, and then around the same time, Edwin Hubble, while he was settling the great debate whether or not galaxies actually existed or not, he was also measuring distances for the same galaxies that Vestal Slipher had actually studied. So Slipher had redshift information, which means he had speed information, and what Hubble added was he actually added the distance information to those same galaxies. And so what Hubble did, I don't know exactly why he did this, but I'm glad he did, was that he combined distance and velocity or speed information from the galaxies that they both studied, and he actually found an interesting pattern. So here's how we can visualize Edwin Hubble's findings between the correlation of speed and the distances to these galaxies. So let's say this is Earth, and this is definitely not drawn to scale in the very middle. And let's say we can draw a 1 million light year radius around the Earth. So anything within the blue dotted circle here, that's basically 1 million light years away from the Earth. So no matter what direction you look, if you find a galaxy there, he found that those galaxies are moving away from the Earth approximately at 13 miles per second. Okay? So now, if you were to go and double this distance, now you go from 1 million light years to 2 million light years. He also found that the speed at which these galaxies are moving away from us also doubled as well, going from 13 to 26 miles per second. Okay? And so now, this pretty much led to the Hubble Law, because the Hubble Law essentially summarized Hubble's observational trends, the correlation between speed, recessional velocity or recessional speed, plotted against the distance. And he concluded that the further away the galaxy, the faster it's actually moving away. And because this happens, no matter what direction you're looking at, the only sensible conclusion that you can come up with to explain why this is happening is that the universe itself is expanding. Okay? And so an application of Hubble's law is trying to address one of the questions that we posed earlier, which is how are the largest structures in the universe arranged? And really this is going to be going into a subfield of cosmology, which is cosmography, mapping out where everything else is in the universe. And so pretty much what Hubble's law allows you to do is if you can get one piece of information, whether it's the speed or the distance, you can get the other. So in this case, if you know the redshift, you know the speed, and if you know the speed, then you can use Hubble's law to figure out how far away those galaxies are. And so from here, then you can use the direction in which you're looking at these galaxies and map out the exact location of those galaxies. And you do this for a bunch of different galaxies, and then you can form a map. And then from that map, you can take a bird's eye view and figure out how are the structures in the universe actually arranged, which is what's shown here. So in this figure, we're actually shown here in the very, very middle, and every single dot that forms this picture as you're looking into two opposite directions is a galaxy. And so from here, now you can tell, right, that the universe has this like web-like filamentary arrangement the further out you're looking. And then you also have these like dark spots, dark regions really where there's really nothing there. Those are called voids. We don't exactly know why they're there or why galaxies don't populate in those regions, but we just know that they exist. And also you can tell here there's a little bit of a bias because basically the further out you are, you might be inclined to think that there's less and less galaxies. But that's more of an observational challenge, if anything, because the further out you're looking, the harder it is to actually detect those galaxies out into that distance. So they appear fainter, which is, makes it difficult for them to be detected by our telescopes here on Earth. Okay, so let's try to wrap our head around this expansion of the universe. There's many analogies presented here, but really each analogy will have its own shortcoming. So that's also important to note. So one of which is called the raisin bread analogy. And so you can see in this picture, you have a raisin bread and you put it into the oven and then the dough itself expands. So in this analogy, the raisin actually represents the galaxies themselves, and the dough represents the space between the galaxies. And so the key idea here is that as the dough rises, the space between the raisins actually increases with time as you put it in the oven. However, the raisins themselves remain the same size. So in the expansion of the universe, at least currently, as the universe is expanding, the galaxies themselves don't get larger because the gravity between those planets and stars and everything within the galaxy is actually enough to keep the galaxy intact. And so the shortcomings of this analogy is that the raisin bread actually has a center and it definitely has an edge, where in reality, the universe does not. Because it doesn't matter where you are in the universe, you'll observe exactly the same thing, which means that the universe is expanding no matter where and when you look at it. So therefore, that means that the universe does not have a center. Because implying that that there is a center to the universe means that you will have a preferred view of the universe where you might get a different result from what everyone else is seeing. And so now here's another analogy. I personally like this analogy better. So this is called the balloon model. And so everything in this balloon, at least on the surface of the balloon, is the observable universe. So all the events that happened historically all happened only on the surface. So nothing actually exists inside or outside of the balloon. And in this perspective, every galaxy within the surface of the balloon sees other galaxies moving away. You don't have a preferred perspective, no preferred vantage point. And also, because everything is on the surface of the balloon, there is no center and there is no edge. Again, that goes back to modeling what the actual universe is really like. There's no preferred vantage point and there's no center. And so something that we assume to be true in cosmology is the cosmological principle. And so the universe is homogeneous and isotropic. That is the key assumption that we hold true when we're talking about the universe as a whole. And so what that means is that the universe is made up of the same stuff and in all different directions, okay? So that addresses both the homogeneity and the isotropic part. And so what the implication of that is that the universe looks the same no matter what direction you're looking at in the grandest of scales. And that's probably something we already saw when we talked about cosmography, right? It doesn't matter where you look, that way or the opposite direction, pretty much looks the same. And again, this only applies in the largest of scales. You can't apply this while you're standing on the surface of the Earth, looking at the sky and directly what's in front of you. So for example, you can't be like, oh, the cosmological principle is not true because the sun is right there, but I don't see the sun in the other direction. That's too small of a scale. You really have to look at a much, much larger scale, the grandest of scales. And so, the cosmological principle can also be applied here in very, very large all-sky surveys. So this is the 2-micron all-sky survey. So in short, we call it 2MASS. And what it is basically a satellite that looked at all different parts of the sky in the infrared. And then from here, you can pretty much, again, doing like cosmography, you can map out the different locations of the different galaxies there and their associated distances. And so in this legend, you can see that the red represents the galaxies that are furthest away from us, and the violet represents the galaxies that are nearest to us. Something else that you can see in this little map that we have here is that the middle here looks like there's a disk or a central lane here that there's no galaxies that appear to exist. And so what that means is that basically you're looking into the plane of the Milky Way, which is blocked by dust, so you can't really see much along that direction. So this is really everything above and below the Milky Way galaxy, and maps all the galaxies from that location. And so the key point here is that the galaxy pretty much, or the universe, excuse me, pretty much looks the same, right? No matter what direction you look at. So you look at this side versus the right side, and you can see that there's a combination of both the galaxies that are close and galaxies that are further away. So same idea here, really, for the cosmological principle. Okay. So something else that I do want to address that is a result of the expansion of the universe is the expansion causes light to stretch. And so whenever we're looking at the spectra of galaxies that are further away, it always appears that they're shifted towards the longer wavelengths. However, I do want to point out that that redshifted light is not due to the galaxies physically moving away from the Earth. That is because the space itself is actually expanding. And so if space itself is actually expanding and light is traveling through space, then that means that light itself will get stretched. And so stretching of the light pretty much means it's going to be going into the longer wavelengths. And so we exploit this idea when we're looking for galaxies that are further away. So this implies that the light coming from the furthest away galaxies will appear to be reddish, or at least tend to be biased towards the longer wavelengths. So here's a picture. This image was taken by the Herschel Space Observatory. And that observatory specifically looks at the reddest colors in the infrared. And so this picture in particular is about 1.3 degrees on one side. So remember, 1 degree, just to give you an idea, is basically the size of your pinky nail held out at an arm's length into the sky. So it's a very tiny portion of the sky that you're talking about. But even with that tiny portion, you can see that this patch of sky is littered with dots. And every single dot here, or every single speck, represents a galaxy that could be the same size or even larger than our own Milky Way galaxy. Okay? And so something that you see as a pattern here is that there is an enormous amount of galaxies, and then a significant fraction of them actually appear to be red. So if you look at this particular galaxy that appears extremely bright in the infrared, when you actually do some follow-up studies on that galaxy, it turns out that that galaxy is approximately 10 billion light years away. Okay? And again, when you're looking at further galaxies, they're going to appear reddish. So we can exploit that fact to actually look for galaxies that are furthest away. Look for the reddest galaxies. That's the basic idea. Okay, so that's pretty much it for how we know that the universe is expanding. And in the next video lecture, we're going to talk about the future of our universe. See you guys next time.